So if you can start yours. Okay, so it's a great pleasure, Guanyu Zhu from IBM, who will tell us about quantum interval applications of generalized symmetries, in particular non-abelian quantum LDPC codes, QFTs beyond manifolds, and applications to universal logical gates. So thanks for joining us, and please take it away.
Cool. Thanks, Sakura, for the invitation. It's nice to present in this wonderful seminar series. So today I'm talking about some application of generalized symmetry to quantum LDPC codes, and it's based on the very recent work together with Ryuhi Kobayashi and Po Shenxing. So first, let me give some introduction and motivation. So the main object we will study is the so-called quantum low-density parity check codes, also called qLDPC codes. So they are a family of stabilizer codes such that the number of qubits participating in each stabilizer and the number of stabilizers that each qubit participates are both bounded by a constant. So here is an example of a CSS LDPC code where there are three type of vertices represent qubits, X checks, and Z checks. And this type of graph is called a Tanner graph. So the condition, the LDPC code condition is equivalent to say that the corresponding Tanner graph has to be a sparse graph. So it's a bounded degree on the vertices. And this definition is basically similar to the notion of a k-local Hamiltonian, which you don't impose that geometric locality, but just the interaction term need to be bounded by some constant k. So then in the classical world, the LDPC code was first discovered in 1960s by Gallagher, but it was only very recently become applied to technology, especially in communications such as the 5G network. So the quantum version of these LDPC codes, they are promising candidates to achieve very low overhead for torrent quantum computing. So it's not for communication, but for computing. So this type of code typically need long-range connection for its implementation. So the related relevant hardware are things like superconducting qubits with a long-range resonator and the multi-layer architecture. So there's certainly being developed in IBM. And also for other platform like AMO system, including neutral atoms, there could be movable qubits. So you can move the qubits around to implement such a long-range connection. And there are other platforms like ion traps could do something similar. So the main reason that we are interested in the quantum LDPC code is that it has a very low space overhead. So let's start with the more conventional codes, which are the topological codes. So they are related to topological order, and the mostly commonly studied one are the 2D surface codes, which are just torical codes defined on a plane with boundaries. So here I'm showing that there are many patches of surface codes, and I define some parameters. First, the total number of physical qubits I call n, and the total number of logical qubits encoded we call it k, and here it's just the number of patches. So each patch hosts a pair of logical x and logical z operator. Then we define the codistance to be the minimal size of the logical operator support. Here it's just the linear dimension. So by a simple geometric calculation, you know that n has to scale as k times d squared. So that's the scaling of the it's called this of the code. And usually we will define the so-called encoding rate to be the number of logical qubits divided by the number of total number of physical qubits. And in this case, it will equals to 1 over d squared. So and d is a distance. So if it becomes infinity, then you have a perfect memory. So in the large d limit, it's perfect, has exponentially small logical error rate. But on the other hand, the encoding rate become 0, or the overhead blows up to infinity. So it's not very efficient for information storage. As long as it become large and good enough. So this kind of code is currently developing at Google. It's on their roadmap. So the alternative option, as we said, is the qLDPC code. So in contrast, it can have instead of a kind of zero encoding rate in the infinite limit, it can actually have a constant encoding rate. So k over n is constant. And it can also have a much larger distance. So in the surface code case, this d scale as a square root n. But for qLDPC code, it's possible to go beyond the square root and distance barrier. And recently, in 2021, it was discovered there's so-called family of asymptotically good qLDPC codes. So where they have the optimal distance, d is linear in terms of logical, the number of physical qubits, and the rate is constant. So the underlying reason for achieving this very nice parameter is due to the fact that it uses some sort of a expander graph structure that has a large expansion, and it's very different from Euclidean space, such that you can have many holes in the complex, and also the systole of this kind of geometry become very large. That can be compared to the entire system size. So this is along the IBM's roadmap. So now we have talked about information storage, and that's recently there are lots of developments. But the next question to ask, how do you do a fault-tolerant quantum computation with these codes? More specifically, you need to find a universal logical gate sets. And it turns out that this has a very close relation to generalized symmetries, and that's realized in recent years. So the basic point is that if you can realize the entire Clifford group, logical gates in the Clifford group, then you add any sort of a non-Clifford gate that will make this gate set universal. So it's in qLDPC code, it's not too difficult to apply Clifford gates. So there's more standard technique like using lattice surgery, and there are also transversal gates where you can do it. But usually it's more challenging to realize the non-Clifford gate. And a very well-established strategy is use so-called match state distillation, discovered by Kitaev and Sergey Bravi like 2 decades ago. The problem of this approach is that it has a very large space-time overhead. So it basically uses very noisy magic state that inject this code and use many copies of the code to distill a better fidelity magic state. And through some iterations, you can prepare a high fidelity magic state, even though your code is not able to do native non-Clifford gate. So the idea here, so in this talk, is that we realize that high rate quantum LDPC codes are not only very efficient for information storage, but it's also highly efficient for parallel production of magic state resources without the use of distillation. So we call this magic state fountain, which is kind of the opposite of distillation. You can directly produce many magic state with high fidelity. And once you get this magic state, you can use gate interpretation to convert them into non-clifford logical gates. So they're useful computational resources. So this is the cartoon for this type of approach. You just try to prepare many magic states. So this represents logical qubits. So then the high encoding rate for the memory, K over N, is turned into a high magic rate. So you have a high rate to produce logical magic states with a small number of total physical qubits. So for example, this idea has recently been developed in these papers, and there are also many follow-up papers along this line. So the previous method we used, including these papers, to produce this match state fountain is to use the higher symmetries, essentially in gauge theory, and they correspond to transversal non-clifford gates, and they are studied in implementing three-dimensional codes, like three-dimensional product codes, and so it has a form like this. So it is with this cup product formulation. And that was first discussed in this paper with Mason's group. So along this framework, there's another notion, which is the higher form symmetry. And in this case, it corresponds to addressable logical gate. So one of the problem in quantum LDPC code is that a single code block can encode many logical qubits. But if you apply some symmetry operator, say if it's a zero form global symmetry, then we'll talk to all of the logical qubits. So it cannot address some targeted number of logical qubits. But the way out is you can use the higher form symmetries because they are supported on a codimension K manifold for a K form symmetry. So it doesn't talk to all the logical qubits. It only talks to, in some cases, the logical operators that has some intersection with this submanifold. So there you can have a targeted logical gate. So this is along the same framework. So this work we will do something different. We use the idea of gauging to measure this type of addressable logical gates, which will correspond to higher form symmetries, or even a new type of, at least we think it might be new, zero form subcomplex symmetries. Here you only need to go to some two-dimensional version of qLDPC codes rather than 3D dimension. So in this context, you won't have a transversal non-Clifford gate. You only have a Clifford gates, but by measuring these Clifford gates, you can effectively implement the non-Clifford gate. And in this context, you can also understand the logical gates as a space-time path integral. So this zero form subcomplex symmetry, its existence due to the fact that we are considering more general chain complex structure rather than manifold. So in a manifold, you only have only one top dimensional cycle that wraps around the entire manifold. But for a general chain complex, for example, here it's like a square complex. You can also subdivide it into a simplicial complex. So in this case, you can see that although this is a two-dimensional complex, it can support many two-dimensional cycles. So they are top-dimensional cycles. So if you have an operator supported on these two cycles or top cycles, they are actually a symmetry only applied on a subcomplex. So that's why we call it subcomplex symmetry. But it's still zero form because the codimension is zero. But you can have many of them. And that's the key, that we can produce many logical magic states in parallel. Basically, each of these subcomplex symmetry will give you measure it, it will produce some independent logical magic state. And this is a picture for the space-time path integral. Okay, so and to get this type of results, we essentially we need to construct the quantum LDPC codes with non-abelian topological order. So here, let me provide some other motivations other than just practical fault-tolerant quantum computation. So one thing is that you can use this to try to understand the general notion of a k-local quantum phase of matter, especially those with non-abelian topological order. And these are not very widely studied yet because there are lots of technical difficulty, as you will see. And you can also try get better understanding of entanglement and complexity from more exotic geometries. So basically, later we will show that this general chain complex, where the underlying the qLDPC codes can be translated into some very exotic geometries or exotic manifolds. And that will lead to very exotic entanglement and complexity pattern. So one example is the so-called NLTS conjecture, and the spell out is no low energy trivial state conjecture, first proposed by Freeman and Hastings in 2013 as a precursor of the quantum PCP theorem. It's a necessary condition for that. And in 2022, it was actually proven to be true. So this NLTS can be considered as a stronger requirement than topological order, where the topological order requires the ground state to be non-trivial, which means you cannot prepare it from a constant depth circuit starting with a product state. Or sometimes it's also called long-range entanglement if you consider you have a geometric locality. So well, for this, it requires all the low energy excited states below certain energy density, all of these states to also be non-trivial. So that's a much harder requirement for topological order. It turns out recently in this proof of this theorem, they used the good LDPC code, quantum LDPC code I just mentioned. And they show that it satisfied this NLTS condition. So it is really due to the exotic geometry, the large expansion of the underlying chain complex that you can have this very exotic entanglement and complexity pattern. So then further along the line, you can have even stronger requirements. So recently in this community, people like Anshu, they are thinking about extend this NLTS framework to the NLTM framework conjecture, which is replace the trivial as a magic. So basically, this conjecture says that there exists certain k-local Hamiltonian that all its low-lying excited states below certain energy density has magic, which means it's not a stabilizer state. You cannot produce this magic by a constant depth circuit from the stabilizer states. So they hence have higher complexity. So even in this framework, you can have non-trivial states in all the low-lying states, but they are mostly just stabilizer states where you can efficiently simulate it classically. While for non-stabilized state, it's usually hard to simulate on a classical computer, so they even have a higher computational complexity. And that is also shown to be a necessary condition of the quantum PCP conjecture, which is an important topic in Hamiltonian quantum complexity. So the other motivation would be to figure out the exotic combinatorial TQFT or gauge theories inspired by quantum LDPC codes. And so for that, I will mention some historical analog. So when we were in middle school, you study Kirchhoff's law on the circuit, which is a discrete subject, and you have like the sum of the current equal to 0 on a node. And then later, when Maxwell developed his theory in the continuum, you can also derive all the Kirchhoff's laws from Maxwell's equation. And right now we have topological quantum field theory, usually defined on a manifold or its triangulation. And in fact, there's already some version of TQFT. They are essentially combinatorial, like Turaya-Viro or Digraph-Wheaton TQFTs. They are already defined on a discrete structure of a triangulation of a manifold. Then you can be more extreme to think about. You can try to define some combinatorial gauge theory that is beyond the triangulation. So that is in the context of quantum LDPC code. So you try to define a gauge theory on a general chain complex. And then you might also discover some new interesting topological invariants from the path integral of this gauge theory. So that's sort of the thing we're considering in this talk. So our goal of this talk is to study a type of a higher form gauge theory defined on a CW complex that has some Poincare duality. So I will discuss how to build this complex later. So they can be think of as a generalization of a simplicial complex, where you replace the simplices with k-dimensional cells, and they are essentially k-dimensional disk, and you attach these cells in an inductive way to produce the CW complex, also called cellular complex. So we will consider to define a twisted higher form gauge theory, Z2P times Z2Q times Z2S gauge theory. And that gauge theory originated from our previous study on a model that realized the first non-abelian self-correcting memory. So it has the action of this form, that it has a standard BF terms and plus a co-cycle twist, basically like a higher form generalization of type 3 co-cycle. So the electric gauge fields here, they are co-chains of a PQS codimension. So the reason that it can give you a non-abelian self-correcting memory is because the excitation in these higher form gauge theories, they are not particle, but they essentially loops of membranes. So you will have some confinement properties to, if you you have a large error, then there is also a large energy barrier to try to forbid it. So that can realize self-correcting. And also here you have the distilled ones are the dual magnetic gauge fields. So here the L where this integral is summed over will eventually become a CW complex. So as we will show that, but in the conventional context one, we can interpret L as the triangulation of a manifold, and that is exactly studied in this previous paper. And there you can also write down the path integral, where the BF terms just impose a constraint that this gauge field has to be co-cycles. So they impose a co-cycle condition. And you have a very simple geometric picture of this path integral in the space-time. That is, there is a triple intersection of the three membranes of the gauge field configuration. So defined on these co-cycles or their Poincare dual cycles. As this, this red is the support of an AP or the dual cycle, and the blue one and the green one. So if you have a configuration that three of them intersect at a single point, then it will give you a minus sign in the sum. So that's the gauge theory we'll try to build. It's one of the simplest non-abelian gauge theory you can realize. So here is our strategy, how to build this type of a CW complex. So we start from a skeleton quantum code defined on a general chain complex, which looks like this. Then we used a mapping discovered by Friedman and Hastings 5 years ago to map this type of a chain complex to a higher dimensional manifold, such as you build up an exotic geometry. And once you have the geometry as a background, you can try to define non-abelian gauge theory. And the original quantum code can be thought as a Z2 gauge theory, but it's used to build this manifold. And once you build it, you can define non-abelian theory. To be more compact, to reduce the overhead, we also further deformation retracted this manifold to a CW complex, which we will explain the details. We will define the previous form of higher form twisted gauge theories directly on this CW complex. So it can be considered as some extension from the triangulation scenario. And finally, we can also pull back the gauge theory defined on this CW complex to the original skeleton chain complex, which you might have no idea how to build it if you directly look at this. So to start, we first construct the type of LDPC code we are considering in this paper. It's called a 2D hypergraph product code. So you start with an asymptotically good classical LDPC code with parameter also NKD. So it corresponds to a chain complex called XX. It's a two-term chain complex. So the one cell is the bit, and the zero cell is the check. And then the boundary map is a parity check matrix. So here is an example. So each row is a particular parity check. Then the column specify the location, the bit location that this check couples to. And the code is defined as the kernel of this parity check matrix or the boundary map, which is also the first homology group. And the code word of this classical code will be just the one cycle in this two-term chain complex. So if you use the expander graph to build this classical code, you can actually realize both constant rate and the linear distance. And then we want to produce a quantum code by take a tensor product of the two chain complexes. So basically, you can compose take a product of this complex in this form, and you will see that the combination of the zero cells in your classical code become the X checks, and the combination of the one cells become two cells, which will be the Z checks in your quantum code. And the qubit is the direct sum of two types of one cell produced by the product of one cell and a zero cell and a zero cell and one cell. So using this product, you now build a three-term chain complex that the qubit is defined on the one cell and the X check and Z check on the 0 and 2 cells. So let's show a simple example with this particular parity check matrix. If you have a classical code with this parity check matrix, the panograph look like this. So the circle and the square are the bit and the check corresponding. Now when you take the product, you basically can combine the check in one code and the bit in the other code. So for the second code, we use a different definition that zero cell is the bit, and the one cell is the check. In any case, you have a combination of the check and bit from the original classical code that give you rise to the check, X check, which is the blue square on the quantum code. And then you have two type of qubits as we explained. It's a direct sum. So you have a bit and check contribution. And finally, you have a Z check, which is shown as the white square. And it's the bit check combination. So it might look a bit kind of complicated, but if you take a special case that the classical code is just a classical repetition code defined on a circle, so then you just produce the toric code, which you are very familiar with. And here, this is an X check of the blue box that coupled to 4 neighboring qubits. And then here, the white box is just the Z checks. It's just here you can have more long-range connections, both in the horizontal and the vertical direction. So
Can
if
I
you
ask a
use
question?
Okay.
So when you do this hypergraph product code, is it clear how the properties of the input codes sort of translate? If they're like good or qLDPC codes, then this hypergraph code is too, or what are the rules here?
So basically, you can first count the number of logical qubits, and here that will be the size of the first homology group, and you get that from the Knud's formula of the combination of the zero cycle and the first homology of the classical code. So in this way, you can see that if I choose good classical code already has constant rate, then this product code produced also have constant rate. It's just Knud's formula. And then the distance, you can lower bound it because to have a logical operator in this product code, its shadow is just the code word on the classical code. So it has to travel at least the length of the classical code to form a closed cycle. So that means it has a lower bound of the size of the original classical code, order little n. And here, capital N is n square of the n. So it will scale as a square root n. So that is similar to the topological code case. Yeah.
Thanks.
So these things we can bound it. So now we want to construct the geometry. So the recipe is that we use the Friedman-Hastings mapping that we first lift the Z2 chain complex built from the classical code corresponding to the classical code to a Z chain complex. So you just lift it. And in current case, since we are lifting the classical code, you can actually just choose a naive lift. You just choose 0 mod 2 lift to 0 and 1 mod 2 lift to 1. And it won't affect your product code. So then, based on this, you can try to build a handle chain complex, which corresponds to a higher dimensional manifold. And here we choose an A-dimensional manifold. And note that we need to shift the dimension of the bit to some higher dimension. The reason of that is that if you want to build a geometry, then you can not put bit on the dimensional 1 because so here the one cell on a general chain complex, it can couple to more than 2 vertices, while on a geometric manifold, the one cell can only couple to at most 2. It can only couple to 2 vertices. So you to change that, you need to raise the dimension of the bit and check. And here we shifted to 3 instead of 2 just to avoid there are some spurious homology in the one cycle that make the analysis more complicated. But essentially, if you use some substituent code idea, you can also do that to have a lower dimensional construction. And it turns out this handle chain complex will have a Poincare duality. So you can see that the left and right part is symmetric. So the dual handle corresponding to the bit is supported on the complementary dimension. So and then now we show how to build this handle chain complex and the corresponding manifold. So we start from the classical code where we have a check represented by the square box. That is the vertex on this hypergraph. And then you promote it to a two handle, so which has the form of S2 times D6. And here I use the quotation mark because it's not a standard notion of a handle, but a type of dress handle that itself is composed of a handle with the same dimension or lower, same index or lower indices. So it's a composite handle. And then we promoted the bit, which is an hyper edge in this chain complex. It's one cell. So in general chain complex, it's not just an edge, but a hyper edge because it can couple to more than two checks. And then you can build a three handle that has the form with a punctured sphere, and then thicken along the extra 5 dimension. And I don't want to go too much details of this conference. You just need to have basically an impression of how it is built. That's probably enough. And then you can then deform it into this more drawing that is closer to your initial structure. And then we attach the three handle to the two handle using the attaching map. Basically, the attaching region of the three handle, this circles S2, actually a sphere S2 that thicken along the D5. So they are glued to the boundary of the two handle. So while you do this, you can build basically the right part of the handle chain complex, which forms a three handle body edge. And to illustrate that, we start with the ternal graph of the classical code, and then you kind of build a three handle body that is sort of a thickened version of this ternal graph. By the way, this extra dimension D5 and all this S2, they only have size order 1. So usually most of the dimension in this manifold is really very compactified. So now we want to also get the left portion of the chain complex, which is essentially the dual handle body. So you can produce that by just take two identical copies of the three handle body you already produced, and you interpret one of them as the dual handles, and then you glue them along their common boundaries. So the handle body still has some boundaries, but when you identify them, you kill all the boundaries that give you a closed manifold. And this process automatically builds the Poincare duality structure. That there's some isomorphism between the homology and the cohomology group with a complementary dimension. So due to the symmetry we building. So a simple example is that you can glue two handles into a torus. So that's similar to what a two handle body to which is similar what doing here.
Sorry, I have a question. When you
Uh-huh.
draw the check with the square with the 4 edges, it looks like it can connect to 4 bits. But then you draw it as the tube with the two S1s. I mean, this is still something that can connect to 4 bits.
So because it's a high dimensional structure, this drawing is only kind of illustrative, so it doesn't look a manifold. But the key is just you find some S2 on the boundary of the two handles, and then you just attach to that. So yeah, so I here actually I have 4 circles, but I cannot draw it just on the left and right boundary because but they have the high dimension. You can
Okay.
in high dimension you can draw it easier. Yeah.
Okay. Yeah, but so we should still think of the check as connecting 4 qubits.
Yeah.
Okay.
Yeah. Yes.
Yeah, sorry, I also had another question on the previous slide where you were talking about the classical code. The fact that K is equal to order N, that's a consequence of the assumption that you're inputting a good code already.
Yeah.
Okay.
Yeah.
Okay, thank you.
Yeah. And they exist. People prove that if you choose some bipartite random expander graph, you can achieve that. And there are also other ways to build it.
Okay.
So yeah. So basically what we have achieved is that we start from a Tanner graph of the classical code, then we build an n-dimensional manifold. Here I only show the half copy of the manifold, which is the handle body. And you can see that the original code word, which is the one cycle on the classical code, now mapped to some three cycle on this manifold. And originally the one cycle is defined on this hyper edge, so it's not really a geometric object. But once you lift it to higher dimension, it actually become a three-dimensional closed membranes. And in general, it maps all the cycle and cocycle in your classical code to higher dimensional cycle and cocycle in the manifold. And here I'm just showing this a Poincare dual pair of 3 cycle and 5 cocycles. So that's what we have achieved. So we already built a geometry out of the code, and then in principle you can already define a non-abelian theory on that. But in order to be more compact and probably also more exotic, we want to further reduce the overhead. So the trick is that you can actually deformation retract this handle chain complex into a cellular chain complex, which has exactly the same algebraic data. But geometrically, you will retract a K handle to K dimensional cell. And in our case, the dressed K handle will be some dressed K cell. So in this form, you just retract its co-core to a single point. So that's the overall strategy. We start Tanner graph and go to manifold, and then we deformation retract. So then each three handle now become the dress three handle becomes some dress three cells, and the two handle become a dress two cells. The two cell here, the dress two cell here is just composed with a single two cell, a sphere attached to a zero cell. And for the dress three cells, it has a basically also a simple structure that you have the two cells on the and zero cells on the on its attaching region, and then there's additional one cells to connect these zero cells together. So this is the additional structure, and it itself can produce some spurious cycle, but if we use subsystem code idea, we can ignore it. So then here, if you build a code on the CW complex, it's no longer a manifold or triangulation of manifold, but so it should be considered as a non-topological code. And another interesting fact is that the CW complex we build in this way will also have a Poincare duality due to the structure of the isomorphism associated with this chain complex. What we obtain is a Poincare complex, a special type of CW complex. Then we can just promote the asymptotically good classical code to code defined on the CW complex. And next, we will consider the product complex, where when we use the Friedman-Hastings mapping, we directly map the skeleton chain complex with the product of two classical codes to a CW complex, which is itself a product of two CW complex produced from the classical codes. And then now we can have well-defined path integral on this CW complex structure. So the reason is that we only use cup product to define a path integral, and it is well defined on a CW complex structure, but it's not well defined in a general chain complex. So that's why we have to do this translation first. you can see that this passing through is actually a topological invariant. First, it has it's a cohomology invariant or equivalently gauge invariant, and that if you add any co-boundaries, it will not change the passing this invariant. So basically, you get some extra terms, which is also a co-boundary. And then to show it is zero, you basically use the Stokes theorem. So that it becomes a d minus one cocycle defined on the boundary of your CW complex. Here it's a space-time complex, in fact. So the key is that the way we build this CW complex, it has no boundary because it's come from this manifold structure. So that can ensure that this extra term is indeed zero, and your passing through is actually a cohomology invariant. This is consistent with the fact that this CW complex only have one unique top cycle, sigma d. So basically, when we say sum over the entire complex, is actually sum over a top dimensional cycle. Okay, so and then we also know that in the manifold case, the passing through is invariant under retriangulation of the manifold. Here we have similar notion of invariance, which you can think is if you subdivide the CW complex. For example, in this case, I'm dividing it into a simplicial complex by adding vertices and the edges to the two cells. And we will still preserve the path integral. It's still invariant under this subdivision. And one important fact I need to use is that there indeed should exist a non-trivial triple intersection in this path integral. So here we can show some example that this can indeed be achieved, and we choose PQS with the corresponding dimension 8, 6, and 3. And so the total spatial dimension of the complex, since each classical code is become an 8-dimensional complex, the total dimension is 16-dimensional. And the capital D is the total space-time dimension. So this is the example we study. And we consider a cohomology basis of these cocycles called alpha, beta, and gamma. And in this talk, we use tilde the notation to denote the basis of in the space-time. Well, those without tilde will correspond to the basis in the space. So then we can consider the following 3 cocycle classes. So according to the Kunus map, it's itself built from the tensor product of the cocycles in the CW complex built from the classical. So you have a product of 2 of them, and then in addition, since it's a space-time complex, you also will answer a single line or circle in the time direction. So you will have a answer product of 3. So basically, it's the space times the time part. So due to the Poincare duality, so we can in the 8-dimensional CW complex, we can always find a pair of cocycles such that their cup product is non-trivial, and the sum of the cup product in the entire CW complex will become 1. And that's really because of Poincare duality. And then you can further add another 0 cocycle in the underlying W complex, and that gives you a triple cup product, which is essentially a triple intersection of the Poincare dual cycles. And similarly for the time part, these 3 things also intersect a single point. Basically, tau 0 it should consider as a line, and because it's a 0 cocycle, and tau 1 is just a single point. And then you can use the Coulomb theorem to represent the cup product of the tensor product of this classical co-cycles into a tensor product of the cup product. So then you can evaluate the cup product in each factor in your tensor product. And we have shown that due to Poincare duality, each of them is a non-trivial, and then you have a non-trivial triple cup product, which correspond to a non-trivial triple intersection. So we actually can build non-trivial intersection structure, and that's important for the logical gate. And also here, the spatial part of this three co-cycle also intersect at a single point. And the spatial part can be the space-time part is this membrane, the red and blue membrane, and their space part is actually these lines. By the way, it's a lower dimensional representation of a high dimensional object, and they intersect at a single point, and which is again intersect with this green membranes in the space part. So that's the intersection structure. Now we want to build our code on this CW complex, and we already write the passing integral. There's a way to translate the passing integral into a non-commuting stabilizer model, which are also called a Clifford stabilizer model. So this type of code has the usual Z type of stabilizer as in the triangulation. It's now just generalized to a CW complex. But then it has some drastic stabilizers. So it has which are denoted by A tilde. So it's a product of A without tilde, and then some additional CZ operator. And there's a corresponding untwisted code, which is 3 copy. We call red, blue, and green. So they have exactly the same Z stabilizers, but their X stabilizers are only a product of X, which is this A without tilde. And turns out the dress X stabilizer is just this X stabilizer addressed by additional CZ term. And you can see that to have well-defined CZ term, we have to have a cup product structure on the corresponding indicator cochains. So it's important to build this cellular structure such that you can make them well-defined. And this model has a property that the stabilizer don't completely commute, but only commute in zero flux sector when all the Z stabilizer has eigenvalue +1. So as I said before, that we can even further simplify this CW complex description to a skeleton chain complex, which is basically the product of an input classical code. I just briefly discussed that. So basically, you have your classical code is mapped to an A-dimensional CW complex. And then you have this part is just your original classical code, which is defined on a Tanner graph. And it turns out that it's the Poincare dual part is just the transpose code, where the parity check matrix is a transpose parity check matrix here. So it has a Tanner graph where you switch the role of check and bit. And then there's a additional part, which is for the 1 cell and the 0 cell. So in fact, we can actually truncate this long chain complex into 3 shorter chain complexes, and to have 3 copies of them, and then still have a well-defined triple cup product structure. So here 0 is so this C1 C0 part actually is a repetition code where the This comes from the zero cocycle of your manifold of the CW complex. So part of that. So let me skip some details, but basically this pullback will map the CW complex, a high-dimensional CW complex, back to a two-dimensional chain complex, where you instead of a longer CW complex, you have three copies of a shorter one, and it's also tensor product of a two classical code. So I have a structured code, and the other you call times a repetition code that is built basically a subdivided version of your initial Tanner graph. So here I'm just subdividing the hyper edge into three edges. And also on this triple of 2D skeleton chain complex. Basically, you can turn the triple intersection of the high-dimensional membranes into a triple intersection of one cocycle or their two cycles. And then you can have a well-defined path integral, which instead of defined on a single CW complex, it's defined on a triple of a two-dimensional general chain complex, but as a much simpler form. Okay, so
Sorry,
now
could
I
you
want
slow
to
down for a second? Sorry.
go
So you're saying this
Oh, okay.
this 16-dimensional thing you can now basically rewrite in terms of copies of 2D codes, right? That's what you're essentially saying. Could you say a little bit more what these 2D
Yeah.
codes are and how you're gluing them together? And could you have constructed them directly in 2D rather
basically,
than going by the
the goal is
16-dimensional?
Yeah, I mean, after you doing this mapping, at least for this example, I also know how to directly build it, but it was not obvious without doing this mapping before. So basically, let me expand a little bit. So basically, what you need is some triple Cabral structure within each classical code, and here it's given by the Poincare duality between the complementary cocycles. But then this star one, if you can actually, you only need the higher dimensional part, like 6 cells, 7 cell, and 8 cell. So you can truncate the low dimensional part and just take a two-term chain complex. So basically, those star ones are the cocycle on the transposed code. And there's an analog of the Poincare duality between the zero cocycle and one cocycle in the transpose code. Because due to the transpose, this one cocycle on transpose code is essentially the one cycle in your original input code. And there is a isomorphism between the one cocycle and one cycle that is the analog of the Poincare duality. Yeah, so
on
by
the
using this
right-hand side, what you've written there just looks like a D4 quantum double. This is what it is, or is it something more complicated?
I mean, it's a bit different as you will see, because I mean the cup product is not the usual cup product. I mean, it's more like a name. Just call this. There's a corresponding trilinear map, but it's different from just the usual triangulation. Yeah. And so you will see the difference in the next few slides.
Okay, thanks.
So okay, I'm running out of time. I'm trying to be slightly faster. But I'm close. So one important properties of quantities in this type of model is the so-called charge parity operator. And here we again start from this high dimensional CW complex description, which is more conventional. And it's defined as the product of the dressed X stabilizers. And as we know that in the untwisted code, this undressed X stabilizer, they will multiply into 1 if this X stabilizer are defined on some p-1 dimensional cocycle. So this is some sort of a high form symmetry, actually. So once you cancel this undressed part, you just get a CZ term left. So basically, we could, in our example that we choose the dimension to be 8, 6, and 3, with total spatial dimension 16. So this charge parity operator is just a transversal CZ operator supported on some 14-dimensional cycle, which is the dual of the two cocycle. And it should be considered as a tensor product of a CZ term on each cells that are supported on this cycle. So it is a high form symmetry, and you can use that to do addressable logical gates in the untwisted code. And also you can rewrite it into the more familiar form with the cut product between the 8 cocycle and the 6 cocycle. And here I put a hat because here I'm considering an operator value the cochains. So they are in fact operators, and they are exactly equivalent to CZ because you can move this sum into a product here, and then it's just tensor product of this -1 to the A and B. And if both of them takes value 1, you get -1 sign. Otherwise, you get +1. That's exactly the definition of CZ. So you can rewrite CZ in terms of this, and now you can. It's also equivalent to a triple cut product if you move this cycle to its dual cocycle. So it has this structure. So in the two-dimensional manifold case, you only have a single zero form global symmetry. That is a single CZ operator acting on copy R and B, red and blue ones, and supported on the entire manifold. So this is the usual two-dimensional case. But now we are going to some higher dimensional, 16-dimensional manifold. We can have many cycle, 14-dimensional cycles. And then each of them will count the charge that penetrating them. So the original case is counting the point-like charge support on this entire space. Now it's only counting the charge, which is now extended object that intersect with the corresponding cycle you choose to define a higher form symmetry. And then similarly, there is also a space-time picture, basically. So this operator is kind of detecting some word line of charge that penetrating it. So let me skip this. Then the interesting thing is that if we apply this pullback from the higher dimensional 16-dimensional CW complex to the two-dimensional chain complex, this higher form symmetry, in this case two-form symmetry, becomes actually a zero form subcomplex symmetry. So it's a support on a zero cocycle. But this zero cycle, its Poincare is a 2-cycle, it's a top dimensional 2-cycle, but it's not the entire complex. To understand the picture is that, for example, you have a 2-dimensional complex, square complex, but you can have many 2 cycles supported in it. So basically, you can think that I start with a high-dimensional manifold and then I compactify it such that those high-form symmetry become this subcomplex symmetry. And the slight difference is that this zero-form subcomplex symmetry is rigid, since there's only one cocycle or cycle representative. You cannot freely deform it. But in the high-dimensional model, it's a high-form symmetry. You can slightly deform it, but because of most of the dimension is quite compactified, you are already deform it in order 1 neighborhood. So it's consistent with this picture. So in general, now I'm showing the key difference from the like the usual 2D manifold model is that yeah, so you can a single edge one cell can couple to many two cells, so you have some book-like structure that either if you have some square complex, you have a square face, then both the horizontal vertical edge can be coupled to many faces. And you will have many two cycles in this structure. And that's exactly what we use to produce magic states. And on this symmetry, the corresponding operator is the CZ operator, will correspond to logical CZ. And finally, we will talk about how to use this symmetry to do non-clifford gate. And we are generalizing basically the gauging measurement protocol from Margarita's previous paper to the quantum LDPC code context. So you start with two copies of an untwisted code, which is Z2 times Z2 gauge theory. And you can initialize the logical qubits in state either plus or zero, which will become a knot to couple and decouple them. Then at time ti, you will gauge the zero form subcomplex symmetry we just talked about. And that will map your original model, the untwisted code, to a twisted Z2 times Z2 times Z2 gauge theory. Although it's defined on a general 2D chain complex rather than a 2D manifold. So you get a twisted code. So the key thing you will do is that you want to measure all the dressed X stabilizers in the green copies, and you get a collection of eigenvalues of these green stabilizers with plus minus one values, or I can rewrite it minus one to the mu, which mu has value 0 or 1. So due to the fact that the subcomplex symmetry of the form of a CZ operator is just a product of this dress X stabilizers. So you are effectively doing a gauging that turn global symmetry into local gauge symmetry, and this is essentially the Gauss's law operator. But this Gauss's law operator only have finite support, so you can measure them for torrently. That's the key difference, because you cannot easily measure the entire global symmetry. Then your circuit depth will blow up, your measurement circuit depth will blow up, you won't have threshold. But if you turn them into a product of a local operator, then you can measure them for torrently. So yeah, basically that's the key. I'm saying that this zero form subcomplex symmetry supported on top dimension 2 cycle is product of this Gauss's law. And by collecting this eigenvalues of each individual dress X stabilizer, you can combine them to infer the eigenvalues of all the zero form sublex complex symmetries defined on a co-cycle basis. So, and then once you've done that, you will then engage this twisted code back to the original code. And the whole process basically achieves a measurement of this zero form subcomplex symmetry. And I mean, depends on your measurement value, it's either +1 or -1. So, and this symmetry operator can be rewrite into the logical CZ, couple two logical qubits labeled by alpha and beta, which have a non-trivial intersection of the support of your CZ operator. So it's again this triple intersection that determines the logical gate structure. Okay, so now I will skip some derivation from path integral, which is just basically
Guanyu, we should probably start wrapping
describe the
up.
same
at
thing,
least to
but
give
within the
people.
path integral picture.
We should probably start wrapping up. But We can ask
Yeah.
questions offline again more, but
Yeah, I'm already, yeah. So I'm skipping, yeah. Okay, now the final slide I will have is that we can use this gauging measurement to realize the so-called our so-called magic state function structure. And basically, previously I have showed that there exists non-trivial triple intersection structure between the co-cycles in the red, blue, and green copy. And then what this really means is that for each green circle, which is a co-cycle, that all the red and the blue qubits that couple to that will be multiplied together into, and then you essentially measure the CZ operators that between red and blue copy that are all connected to the same green co-cycles. So it's still a bit messy, but you can, if you want to get a clean, independent magic CZ states, you can actually turn off some of the logical qubit in the red copy into logical zero. So then you will have a separable triple intersection structure. Then for each green co-cycle, a zero co-cycle, you can just find a single pair of logical qubits that is acted on. And that will produce a product of destroying the CZ magic states. And here is the definition of the CZ magic state. It's just the +1 eigenstate of the measurement of a logical CZ acting on these two logical qubits. And it has a form of 0, 0 plus 0, 1 plus 1, 0. And essentially, your measurement procedure project out the 1, 1 component. And on the other hand, if your measurement result is a -1 on this operator, then you just get a product state. You will just throw it. So with high probability, you can get many logical CZ gates. So in fact, we can, with n qubits, we can prepare square root n disjoint CZ magic states. And the distance that we said in the beginning is also square root n in the product code. And this whole process take all the DROMs of measurement. So in contrast, if you use a topological code, like a surface code, you can do the same thing, but you only produce one magic state. Okay, here the summary. So basically, we develop a combinatorial non-abelian gauge theory for quantum LDPC codes defined on CW complex, or further pulled back to some general chain complexes. So and we get some topological invariant on this general chain complexes. And an interesting discovery is a new type of zero-form subcomplex symmetry that for gauge theory defined on general chain complex instead of a manifold. And in fact, you might feel that this subcomplex symmetry is very similar to subsystem symmetry. It's both, they are both rigid and they are act on some subsystem of the underlying space. And I think actually when I discussed Vedika and David, they told me there's some construction that it's essentially equivalent to the subcomplex symmetry. So my conjecture is maybe most of the subsystem symmetry can be understood as some subcomplex symmetry on some general type of chain complexes. So the gauging measurement of addressable logical Clifford gates on this subcomplex symmetry will give you magic states. And there's some outlook. We also need to work out the decoder for LDPC code. It's already worked out in Margarita's paper for topological code, but for the LDPC code, it's much more complicated, and we also need to prove autonomous there. So another goal is that we want to search for non-abelian or Clifford stabilized qLDPC codes that satisfy the NLTS property that not only the ground state, but all the low-lying states is non-trivial. At the same time, it has a non-abelian topological order. And it might also satisfy this NLTM conjecture where all the low-lying states contain magic. So to achieve that, you might need to build a more exotic underlying chain complex that has a distance, probably linear distance. And finally, maybe the quantum PCP theorem, which computer scientists are mostly interested in, is just some sort of a version of exotic topological quantum field theory. At least in the case of LTS, it's just an exotic Z2 gauge theory defined on very exotic geometry. So maybe this is the same for the quantum PCP. Okay, so that's all of my talks. Thanks for your attention.
Thank you very much. Yes, very nice. So how, implementation-wise, how easy is this to implement compared to like something like a surface code?
Oh, so for the code itself, it's I mean, people are working hard, at least IBM and some other companies building very large code. So it needs a long range transmission line, but it's already being developed. So I mean, actually we're quite ambitious on that. So maybe in 2028 or 2029, you will have some large demonstration of this type of codes. Currently, IBM study a particular code which is called bivariate bicycle code, but it's essentially a generalization of the hypergraph product code, which can be considered as a balanced product of classical codes. So when you take broad, you add some twist, and you will get an even more compact code with even larger distance. But this kind of techniques can definitely be applied to that. But I guess the main worry about practicality is that the model itself is slightly more complicated than Pauli stabilizer models.
Sure.
It's all these large bit Clifford stabilizers, and the decoder is also more complicated. So that might limit its I mean, if you want to make a practical, there's some barrier. But on the other hand, for some other approach, which I mentioned in the beginning, where you directly apply transversal gates, non-Clifford transversal gates, and I think that might be easier to be realized. So because they are only acting on Pauli stabilizer codes. But they need to have a high dimensional product structure. So the connective is a bit longer, but since your setup is already non-local, so the difference between 3D product and 2D product is not as huge as a 3D manifold and 2D manifold. It will only allow nearest neighbor coupling.
Right.
I
see. Yeah, the other questions. Okay, we went quite over time, so I think people might be exhausted. But so thanks very much. I'll stop the recording.